Thanks very much. Recording progress. Thanks very much to the local and remote organizers for inviting me and putting together this winter school. This is actually quite special for me because my first ever conference was here in Bedlevo many years ago. We were actually in a different room, which is why when I saw this, I thought, oh, I'm not actually going to the same place. They've changed their building completely. I'm really old. But no, I was actually in a different room. So it's really great to be back here. Okay, so my plan, I have two sessions. And I said I would talk about groups acting on trees. And so I have to warn people when I say groups acting on trees, most people think Basset theory. I'm not going to talk about that. There are many courses about Basset theory. This is a different course. And I've split I split the content into two parts, which I'm not sure will be of equal length. So the first part is groups that act on rooted trees, and the second part will be groups that act on unrooted trees. Okay, so part one, groups acting on rooted trees. I'm going to start always assuming that D is an integer at least 2. D stands for degree. And boldface D is going to be an alphabet of D symbols. And I've just written the numbers from between 0 and D minus 1, and I've underlined them because I wanted to be clear that they are symbols. They're not numbers. I'm not actually counting anything. And D star, boldface D star, is the free monoid on D, the free monoid generated by D. So that's just all possible finite words over the letters, over these symbols. And the operation is this concatenation. There's no reduction in a monoid. There are no inverses. And I'm going to identify it. I'm going to identify it with its right Cayley graph. So here's a picture of the right Cayley graph of this free monoid when D is 3. So why is it a right Cayley graph? Well, I start out with the empty word, which is the identity of the monoid. And then I put the generators of the monoid, which are the symbols 0, 1, 2. And then next to, below each of them, for some reason my trees go downwards. I did spend time in Australia. But I think this is a computer science thing. I don't know. And then next to 0, I put what I obtained from 0 by adding a generator. Okay, so that's so everyone sees what the picture should be. Great. So if I write D star, I really mean the graph, the tree. I won't mean the monoid, I will mean the tree. Okay, and just a bit of notation. D to the N will mean words of length N, and this might be important. D to the infinity will be infinite words. Words of infinite length. These actually don't live in the tree. This is the boundary of the tree. Okay, and the group that we care about, the most important group is the group of all isometries of D star. That really is just the group of all graph automorphisms of D star. By graph automorphism, I mean, it's a bijection that takes vertices to vertices, edges to edges, and preserves adjacency. So because the root is the only thing of degree D, everybody else has degree, well, a degree valency, however you want to call it. The root is the only vertex with 3 neighbors, or D neighbors, and everybody else has D plus 1 neighbors. So the root has to be preserved. And of course, if the root is preserved, then everything at distance 1 has to stay at distance 1. So the only thing I can do is move these around. And then I might be able to move these, or these, or these, and so on. Right? This is the group that we care about. And I've called it, most people call it automorphisms, but I I didn't want it to get confused with automorphisms of the monoid as a monoid. And also, I like isom because it really is isometries of D infinity. So if you put a metric, you can put a metric on D infinity, where the distance between two infinite rays is, say, 1 over d to the n, d to the minus n, if they last agree at level n, at distance n from the root. So with that metric, this really is the group of isometries of D infinity. Okay, so that's what, yeah, question? Yes, but yes, it is. If you know about this, it is the inverse limit of all the permutations, but I don't want to talk about inverse limits yet. Okay, what else did I want to say? Okay, the first observation is that this tree is self-similar in the following sense. Is self-similar in the following sense. If I define, so for every vertex, so that's a finite word, I can define the following map. Now I hesitated as to how to define this. So I decided in the end to go from VD star to D. So this is all words beginning with V. And I can define the following thing. If my word begins with V and then it's W, then I just remove the V. Okay, and this thing is just, well, okay, here are all the words beginning with 0. If I just remove the first 0, then I get all the words. Okay, so this is a graph isomorphism. And this carries over. How can I write this? I'll write this here. I'm doing the same thing as Hannah, trying to find space. This carries over to isom D star. So if I have a phi, an automorphism of this tree, then I'm going to define phi sub V. So this is what? This is this right? Yes. Okay, I'm going to define a new automorphism of the whole rooted tree. How? Well, I first do IV inverse, so that means putting a V in front of, right? So that means if V is, say, the letter 0, then I look down at this subtree. Then I do my phi, whatever it does something. Phi will take this subtree possibly to itself, possibly to this subtree, let's say. And then within this, it might still permute the vertices. Okay, so I've taken this subtree here, I've permuted the vertices, but now this subtree is also isomorphic to the big tree. I just need to remove the first one. So removing the first one, and one was where phi took my 0, my first integer. Okay, so basically what this says is if phi took this subtree to this subtree and did something in there, phi sub V or phi sub 0 is what did phi do to this subtree? The mixing. Okay, so this is an element in isom D star. Right. Okay, so what does this say? This says that the group of isometries of D star acts on the left of D star, but D star acts on the right of I sum D star. What do I mean by this? Well, I mean that, well, maybe this can be a little exercise to use this definition to show that if I look at phi sub v1, that's a new automorphism of the tree that I obtained, and I do that for some other word v2, that's the same thing as doing it for the concatenation. Okay, so that tells me, right, that's part of the definition of a semigroup action. Also, the fact that if I have two tree automorphisms, two isometries, and I look at I'm going to call this a section. I look at their section, the section of their composition at V, then this is, well, it's the section at whatever I did first, which was psi, followed by the section of phi, but not necessarily at V. It will be at wherever psi took the first letter, wherever psi took V. And the last thing, so this is point 1, point 2, and point 3. If what's the section of phi inverse? Well, it's the section of phi at phi inverse V, all inverse. So the thing to notice about this is that taking this section of V is not is not a group homomorphism, right? Otherwise it would have the same V here. So it's only a group homomorphism if psi, well, why? If psi fixes V. Yeah? No? Okay, so taking the section at V is only a group homomorphism from the stabilizer of V. It's stabilizer, this notation is clear, right? For stabilizer. Okay. Right, we'll say, so now comes the definition. A group G of automorphisms of this regular rooted tree, so a subgroup of isom D star, is self-similar. Right, this whole exercise was to show that the tree is self-similar, and this carries over to groups that act on it. So it's self-similar if for every V in D star, so for every word or for every vertex in the tree, however you want to see it, the section of my group at V, so that's phi sub V, where phi is in G, is contained in G. So that says, right, there's so supposing my my group was simply doing this a 3 cycle here, and maybe maybe swapping these two. Suppose my group is just, I do a 3 cycle here and I swap two ends. If I look at the section that is the group generated by that thing, if I take the section of that element at this subtree, what I obtained is the thing that swaps these first two edges, and that's not in my original group that I chose. So this being self-similar is really saying something, right? Just because, so the sections don't need to be, again, things that you had at the beginning, elements that, like if you have a certain restriction on what you can do at the root, the sections might do something else that's not what you decided that you would do at the root. Okay. I'll give examples later. More examples are coming in case this is not clear. Okay. Um, right. So in other words, G is invariant under the D star action. In some sense, you could say it's a tree analog of being shift invariant. We've seen shifts during the week, and we will see more shifts during the week, I imagine. So this is if D were equal to 1, then we would just have a line. My tree would be an infinite line. So this is the higher valency version of being shift invariant. Okay, so examples. Examples of self-similar groups. Well, obviously, the first example is the whole group of automorphisms of the tree, and of course that's I already said it, right? Because this phi sub b is still an automorphism of the whole rooted tree. So of course it's self-similar, but that's not the reason I'm going to say this. It's because I also want to introduce some notation. So every element, every phi in isom B star can be written as in the following way. So phi is, I'm going to write it as some sigma, phi sub 0, phi sub 1, blah, 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 up to phi sub d minus 1. So what is this? This is some element in some permutation of the d vertices at the first level. And then this is, well, these section maps. So basically what I'm saying is that how do I describe an automorphism of the rooted tree? Well, I first say, so remember, this is acting on the left of the tree. So I'm doing this first. I'm doing this tuple first. So this means I look at my element of the tree, I look at my vertex of the tree, and I say, what letter does it start with? So it starts with a 0. So then I leave the 0 as it is, and I do phi 0 to the rest of the tail. And the same thing to the rest of the letters. Right, I've permuted all the trees below in this way. And then I might have to permute each of the things at the first level. I'm never sure what silence means. I can at least look at faces, so that's good. If you have questions, then please interrupt. If I haven't made something clear, please tell me. Okay, so these things all live in isom B star. So this means that isom D star is isomorphic to sim D, semi-direct product, isom D star to the D. So D copies of isom D star acted on by the symmetric group on the number of symbols. Okay, and this is just the wreath product that we saw. We saw it yesterday in this talk with the lamplighter group, the wreath product. So I'm going to write different notation. I'm going to use different notation because Hannah used it the other way around. And this is the strange notation. I'm the one that's strange. So usually when you write this symbol, or even the symbol that I wrote before, it means that this is acting on a set, and you have as many copies of this group as the set that this is acting on. I'm doing it the other way around. So for me, I'm always acting on the left. So the left group is the one that is acting. Okay, so this is why I wanted to go through this example, because because notation. More examples. More examples. I sum fin. This is all the phi in I sum d star. So finary automorphisms. Where's the halfway? Here. So these are the finary automorphisms such that there exists n, some natural numbers, such that for all v in dn, phi v is the identity. So these are the automorphisms of the rooted tree, such that I might do something up to whatever level, and then I stop. I won't keep permuting things forever down below the tree. Okay, this is of course self-similar because, well, if this holds, then you push things down, the n will only get smaller. That this n will only get smaller. Right. What is this? This is, if you think about it, this is the directed union of iterated symmetric groups. Wreath sim d n times directed union n. So what is this? I'm going to do it for 2 because my pictures will get too big. So I start out. So sim 2 is just well, I don't know. The only non-trivial thing is this. I inject this into the wreath product of sim 2 with itself. So that means 2 copies of the symmetric group and another copy of the symmetric group acting on top. Okay, so this means that the wreath product of sim 2 with itself is the automorphism group of a tree of height 2, a binary tree of height 2. The wreath product of that of three times the wreath product. So sim 2, wreath sim 2, wreath sim 2 is, well, I have the first one that I had before, and then I have as many copies of sim 2 as things that I was acting on. So for each of these things that I was acting on, I put another copy of sim 2. Okay, so suppose I have this. How do I inject it into here? Well, I just do this and nothing below. That's a perfectly valid element. And then the same here. Suppose now I had something there, then well, I just keep doing it there and nothing underneath. Yeah, okay, so this is right. If it's a directed union, I'm supposed to tell you how they fit into each other. This is how they fit into each other. And this also, so this is an example of a self-similar group, and it satisfies something stronger, right? This also satisfied the stronger thing that the group was isomorphic to the wreath product of itself with a symmetric group. This is also true for this group. Okay, more examples. Non-trivial, a less trivial example. So I'm going to call Z the group generated by a phi, which I'm going to write using this notation. This is why I spent some time to find the notation so that I can use it. So this is going to be, I do some sigma first. Well, not first, I do it last. In fact, I write it first, but I do it last. And on each subtree, I do the identity, except on the last one where I do phi. And this is the subgroup of isom d star. Let's do it for and sigma. I should tell you what sigma is. Sigma is this d cycle. So let's do it for d equals 2. Phi is I permute the 2 trees at the top, and if my word starts with a 1, then I I do whatever phi was below it. So the picture is I last swap these two things. On here I do nothing, and on here I do phi. So that, what was phi? Well, I swap these two things. Here I do nothing, here I do phi, and so on. What is this element? What does it do? Well, let's also see what happens to a word that begins with a 0 will now begin with a 1. And now I'm supposed to do phi sub 0 of W. But phi sub 0 of W is the identity. Okay, so this is just, I've changed the first letter. All I've done. If it starts with a 0, I just change the first letter to a 1. If it starts with a 1, I change the first letter to a 0, and then I do phi 1 of the rest of the tail. So that's 0, and what's phi 1? Well, that's phi. Okay, so this is saying if my word begins with a 0, I just change it to a 1. If my word starts with a 1, I change it to a 0, and then I keep looking. And then I keep looking. If the next word is if the next letter is a 0, I change it to a 1 and I stop. So let's see what happens to okay, so this will go to 0, 1, and this will go to 0. Then I have to do again, right? So that's a 0, and this is finally a 1. What does this look like? This looks like something. Exactly, this is the odometer. So this is the odometer. So it's adding 1 in base 2, except that for some bizarre reason, I am writing higher powers of 2 on the right instead of on the left. Okay, I chose the right calligraph instead of a left calligraph. Okay, so this is isomorphic to Z, which is why I chose Z as my letter for the group. And of course it's self-similar because right, what do I have as my possible sections? Well, it's phi, which is the generator of the group, or the identity. Of course it's self-similar. Okay, so here's a self-similar action of the integers. Maybe I'll use the space. No, I'll use the new board. I'll use the new board to say that self-similarity doesn't necessarily pass to subgroups. Being right, so I wanted to. So what's special about self-similar groups? Being self-similar or having a self-similar action is a property of an action. So the same way that you say a group is linear if it acts faithfully on a vector space. So this is saying that a group acts faithfully on a rooted tree in this special way. But of course, it's a property of the action. You can embed a group into another one in possibly many different ways. And so just because you have an embedding of a group doesn't mean that a subgroup, the type of embedding is preserved. So I'll make myself clear with the example. So let's have D generated by A and B, and this is a subgroup of isom 2. And what are my elements? So A is just the finite tree automorphism that swaps the two subtrees at level 1 and doesn't do anything else below. And B is going to have a recursive definition, so like the odometer, but it's slightly different. It's A and then B. So A is simply this swap, and then do nothing else. And B does this swap, and then does B again. So I have to do this, and then this, and then that, and so on. Yeah. Okay. Okay, so clearly, so first of all, let's see, what is this group? This is clearly self-similar, right? By definition. by definition of B. B is what guarantees that it's self-similar because all the sections are A and B. Okay, so what's the order of A? Well, it's just a transposition, so the order is 2. What's the order of B? All I'm doing is transposing, right? So if I do it twice, then it's also the identity. Right, so I've got a group generated by 2 elements of order 2, and I've called it B. That gives you a big clue as to what it might be. Guesses? What's a group generated by 2 elements of order 2? Yes, exactly, dihedral group. Thank you for audience participation. This is good. It would also have been okay if you got it wrong. It's nothing. This is confusing at first, so it's hard to know. Okay, so let's confirm that it's the infinite dihedral group. We have to look at the order of AB, right? The product of the 2 elements. So we want to say that AB has infinite order. What is this? Well, let's see. What's AB? AB is doing this swap. Well, it's first doing this and then doing the swap. So I'm going to square it. I'm going to square AB. So this is 0, 1, AB, 0, 1, AB. And the thing about how do you operate in these real products, I want to push this over to the other side, and I could do this at the expense of acting on here like this does. Okay, so this is easy. I don't have to worry about, oh, is it acting in this way or is it acting in that way? Because it's a thing of order 2, so fine. So 0, 1 times 0, 1 is nothing. And then I swap the order of these. So this is BA, AB, BA, AB. Aha. Okay, this tells me that AB to the 2n is BA to the n, comma, AB to the n. Right, so the first thing is AB cannot have odd order because if you have an odd number of times AB, you have an odd number of A's. So that means you've done the swap an odd number of times, and that's not the identity. Okay, so I need to worry about even powers. If it had even order, then this would be the identity. AB to the 2n would be the identity. But then that means that these 2 things would have to be the identity already. So 2n is not the order is n. Contradiction. So this tells me that the order of AB is infinite. And in fact, I have, of course, that if I conjugate AB by A, I have BA, which is, of course, B inverse A inverse because A and B have order 2. So this is AB inverse, right? So this tells me that D is the infinite dihedral group. Let's look at H, the subgroup generated by AB. The subgroup generated by A, okay, it's generated by AB, so that means what's AB? It's this thing. What are the sections of elements of H? Well, the sections of the generator are A and B, but neither A nor B is in the subgroup generated by AB. Okay, so this is not self-similar. So A and B are not in H, so that means that, right, so AB, let me write it this other way. And neither of these are in H. Okay, so being self-similar doesn't necessarily pass 2 subgroups. Of course, but I just gave you a self-similar action Z right before. So this just says that you have to be careful about how you are self-similar or how you define the action. Okay, let's modify this group to get something more interesting. Well, I'll write it here. Let's modify. So it's now capital G, and it's generated by A, B, C, and D. And now B is going to be, okay, I'll leave it like that. AC, and I have to tell you what C and D are. So C is A, D, and D is identity B. So the picture, okay, so now B, the new B, does something different. Because it does, okay, it still does A here, but then it does C. Okay, so what does C do? It does A on this first subtree, fine, and then it does D. All right, but then D does the identity. So I'm doing something different. It does B here. So now the pattern repeats. I do along this spine, swap, swap, nothing, and then repeat. Swap, swap, nothing, swap, swap, nothing. Of course, C and D are just shifts of B. So C is the one that does swap, nothing, swap, swap, nothing, swap, etc. And D starts by doing nothing and then does swap, swap. Okay? So this G is of course self-similar. And of course, and it's still generated by elements of order 2, right? All I'm doing is swapping. Okay, so it's generated by elements of order 2. I still claim that G is infinite. Why is it infinite? Because if I look at the stabilizer in G of which letter have I chosen? 1. The stabilizer in G of the letter 1, well, A definitely doesn't stabilize it, but B, C, and D do, because they don't do anything to the first level. So B, C, and D, but also the conjugates of B, C, and D by A. And in fact, that's everything. Exercise. So this is this has index 2. Of course, it has index 2 and G because it's the stabilizer of, if you stabilize this point, then you have to stabilize the other point. So it's in fact the kernel of the action on the first level. So that's why it's an index 2 subgroup. And if I look at, and I claim that this maps onto G. How does it map onto G? Well, what's the section of B at 1? There's the section of B at 1 is C. The section of C at 1 is D. The section of D at 1 is B. So now I've got my consonants. And the section of ABA at 1, well, what's ABA? ABA is just taking the definition of B and swapping the two entries. So that's BA section at 1. So that I've done it wrong. No, yeah, I've done it correctly. I was looking at yes. Okay, so I've got my 4 generators. So I've got an index 2 subgroup that maps onto the group. You cannot do that in finite sets. So G is infinite. And in fact, G stands for Grigorchuk, who proved in 1980 when he introduced this group that G is a 2 group. So every element has order a power of 2. I'm not going to show this. I'm going to show it because this is available in many places. I've decided to do it for a different family. What time did we start? Okay, I'm going extremely slowly. There's a reason why I chose to draw the three regular tree, because I'm going to use it. Okay, so maybe I should talk about the history of this. Maybe this doesn't surprise anyone, but this is very surprising. But a group generated by finitely many elements of finite order, and all the elements have finite order, and you somehow manage to have infinitely many of them, how do they not all collapse into something finite? Right? So this is Burnside's the general Burnside problem. Burnside asked it in the 1900s. And so it took around 80 years to find an answer that I could explain in a few minutes. Well, I could describe the group, and I'm going to prove it for another answer to this problem. Yes, yes, A is finite. Any proper subgroup, if it's finite, yes, this the thing generated by A. I mean, anything generated by a single element is finite. No, I don't understand the question. Yeah. All proper subgroups are finite. No. For example, this one. This has index 2. In fact, it turns out that for this group, uh, all proper normal subgroups have finite index. The opposite, yes. What was I going to say? I was going to, yes, introduce another example. So this is the Gupta and Sidki. So this was introduced in 1983. P at least 3 is a prime. And so let me just call it G sub P. This is generated again by A and B, and it's a thing that acts on the P regular tree. And what does A do? A is the same thing as the previous A. A is a P cycle. And B has this recursive definition where it doesn't do anything to the top level. And on the subtrees, it does A inverse, identity, identity, and then B. So let's do it for P equals 3. For P equals 3, let's say this is A. A is just this 3 cycle, and B is in blue. So B does this 3 cycle in the other direction, and then B again. So that means doing 3 cycle in the opposite direction, and so on. Keep going down forever. It's similar in spirit to that, but it gives a different thing. Okay, so it's of course self-similar by definition, and it's also infinite because now I've chosen the letter 0. So the stabilizer of the letter 0 maps onto GP. It's the same argument as before. And I'm actually going to show that it's a P group. So this implies that GP is infinite. Okay, I'm going to define some notation. So B sub I in square brackets is going to mean B conjugated by A to the I. So let's do it. So let's just do it for P equals 3 because this is what is going to make my life easiest. So B0 is just B. So that's A inverse B. B1 is B1 is AB A inverse. Okay, and if you do the wreath product calculations, then you should have, right, so this permutation sends 0 to 1, so I should have the section of B at 1 here, and the section of B at 1 here is that what I wanted, or is it the other way around? No, I should have I should do A inverse, which takes 0 to P minus 1. Okay, so this is B, A inverse, and B2 is the other one. Okay, I'm writing this down because I'm actually going to prove, I'm going to use this to prove that this group is a 3 group. I'm not going to prove it, I'm going to give you an idea with a few chosen examples. So let's see why G3 is a 3 group. Sketch. So I need to show that every element has order a power of 3. And for this, I'm going to induct on length, and by length I would mean, well, the first thing to notice is that every element of G, well, I'll say 3, but it's true for P, you just have to make the appropriate modifications, can be written as A to the something, some power of A, followed by BI1 to the, I don't know, K1, BI2 to the K2, BIN to the Kn. And the way you do it is, right, you have your word in powers of A and powers of B, and you just collect the A all the way to the other side by conjugating. So here I just obtain conjugates of B. It's as easy as that. Really, this is an element of the free product of A and B. I'm doing this in the free product, but of course the free product maps onto this G3. So in particular, every element can be chosen like this. And this is going to have syllable length n independently of this power. Right, I'm going to say that if I have an A or if I don't, it doesn't matter. These 2 words of this form have the same syllable length. Okay, so I'm going to induct on the syllable length. I should give at least one proof, right? If it's a mini course, I should give at least one interesting proof, not just that whatever group is the dihedral group. Okay, so induct on length of shortest representative of G in G3. So length at most 1, just so that we get an idea. Well, length at most 1, it's some power of A, which of course has order 3, some power of a conjugate of B, which of course has order 3. And then there are things of the type have order 3. And then there are things of the type, what if G is of this sort? Right, that's a thing of length 1, right? Because there's only one B. That's basically the length. How many B's? Okay, well, let's see. If I cube this element, but why do I want to cube it? Because I want to get rid of the 3 cycle at the top and look at the sections. The sections will tell me the order of the group element. So if I cube this, I get A, B, A, B, A, B, and collecting all the A's, this is A, B, I can write this as A inverse A squared B, and this is +1, which is -2 modulo 3. Okay, so that's this, and then for this is B1, B2, B0, which I conveniently wrote down over there. So you can look at the other board, whereas I can't, I have to look at my notes. So this is BA inverse A, AB, A inverse A, B, and all of these things have length 1. So they have well, they don't just have length one, they're actually, so this is in fact B, um, B, B1, B, which of course has order 3. Okay, so that tells me that the order of G is 9, right? Because I had to cube it to get something of order 3. I cubed it and I got something of order 3 because they were just B's or conjugates of B. Let me give you an example of the inductive step. Okay, well, inductive step. So let's do something of length. Let's do something of length 2. So G is going to be, I've chosen it carefully so that things work out. I've chosen it to be this. Let's do the same. I can't directly look at the sections because I've got this 3 cycle at the top doing stuff. So let's do the same trick. G3. Well, let's use the same trick as before. If I cube this, then I'm going to end up with the B's that I had first conjugated by A, then conjugated by A squared, and then the original stuff. So this means that first I add 1 to the subscripts, then I add 2 to the subscripts, and then I leave the subscripts the same. So that's B2, B1 inverse, B, I add 2, so that's 0, B2 inverse, and then the same, so that's B1, B0 inverse. And since you helpfully have the list up there, I will look at my notes. If you work all this out, this is A inverse, B inverse, A, B, A inverse, B, A inverse, B, inverse A, and A, B, A inverse B, if I haven't made a mistake. Which turns out to be, if you collect all the terms, well, you can just look at it. There's going to be here, there are two B's separated by A's that don't cancel out. So this will have length 2. Again, 2 B's separated by A's, length 2, 2 B's separated by A's. So length 2, these things have length 2. So they have order 3 to the sum by induction. So G will have order 3 to the 1 more. No. Sorry, I got ahead of myself because there's a problem. Somebody should have complained. Why? I said length 2 and I was happy. I shouldn't be happy. What's the length of the element that I started with? I started with an element of length 2. I haven't actually shortened the length. I can't use induction. Okay, well, let's see. So I actually have to write out what these elements are. Let's see. Let's look at my helpful calculation. So this is B2, B1, B0, B1 inverse, and B2, B0 inverse. Okay. Ooh, but this is good because these things now don't have any rogue A's. So I can just look at all their sections at the same time. So let's look at, for example, this one. So this thing is, if you then look at its sections again, this should be an inverse, right? This B is inverse. So if you look at this is AB, this whole thing here. This is AB, B inverse A inverse, A inverse, and that has short length. This has length 1. Order 3. So, and you can imagine that I will do the same thing to these other two. So these things will have order 3, and therefore, right. So what am I saying? Each of these, this has order 3, and therefore this has order 9. Or well, I might have gotten. No, I'm not so confident about the powers, but anyway. So this means that G has the order of G is 3 to the something, which is what I needed to do. Okay, so what's the general gist? If I have my group element given to me in this form, and it's got an extra A, then I cube it. And what's going to happen to the sections here? Well, I'm going to have essentially as so each okay, I'm going to have as many B's as I had above. Why? Because so B1 contributes a B to this position, right? But I'm going to have B1, but also B2 and B0 coming from this because I've cubed it. I've conjugated it by all the powers of A. So this B is going to contribute the B that it has to each of the positions. And the same is true for all the other B's in my word. Okay, so the length of the sections of this G cubed is at worst the length of G. Okay, but that's okay because it will end up being something without A's eventually. Eventually will end up being something without A's. And then if it's something without A's, then how many B's does this contribute to each of the section? Well, to each coordinate, it only contributes at most half of the B's. Yeah, because the worst thing that could happen is that this is an alternating word, B2, B1, B2, B1, B2, B1. And so in this coordinate, the only B's I will see will be the ones that come from B1. The B0 only contributes a power of A. So that reduces the length. And that's the idea of how to prove this. Okie doke. I'll finish with some remarks. Well, I'll finish before the break with some remarks. So G2 and these GPs are not linear. They're not linear groups. Okay, I want to argue that they're not groups of the type you've seen before. A, because you've probably never seen these kinds of calculations. B, because you've probably seen linear groups, hyperbolic groups, this kind of groups acting on spaces that people are used to, not trees. So just to say that these two groups are at least not linear because there's a classical result by Burnside, Sure. This is from the I don't know, I'm going to say 1910, I'm not sure. And then Kaplansky much later, and I don't remember the year of Kaplansky's result, that says that every finitely generated torsion subgroup of GLNK is finite. And so this was proved by totally by Burnside and Sure for K of a field of characteristic 0, and then Kaplansky proved it for any characteristic. So torsion means every group element has finite order. So this is saying an answer to Burnside's question does not live inside linear groups. Also, why is G2 special? G2 is famous. I didn't call it G2, I called it G. Well, it's famous not only because of this, it's also because it's the first known example of a group of intermediate word growth. People are nodding, so people are familiar with this, right? Good. And And also, maybe I'll make a last comment here before the break. The last comment I want to make about okay. So G2 has intermediate growth, but we don't know about the growth of GP. It's larger than polynomial because it's not virtually nilpotent, but it might be exponential. We don't know. So there's an open problem if you want to work on something. And you can see it's a very concrete group. You can I really got my hands dirty and did calculations with you. So go and calculate stuff with this group. And okay, so the result, this is by a result of Bartoldi, Kajmanovic, and Nekrashevich from this. Did I write down the year for this? Yes, 2010. By a result of those, well, I'll write that GP is amenable. Of course, G2 is amenable because also, but that's because of sub-exponential growth. So the Fulner sets or the Fulanitsky-Reiter criterion is given by the balls of finite radius in the group. But so the result of these three implies that GP is amenable. Okay, so that's nice, and it's actually done using random walks. So pay attention to the random walks course, but they're not elementarily amenable. And this is by a result of Ching Cho from 1980 that says that all torsion groups, all torsion elementary amenable groups are locally finite. Locally finite means direct union of finite groups. So a finitely generated locally finite group is finite. So these things are not, so elementary amenable, I don't know whether everybody knows what it means. It means you start out with finite groups or abelian groups, which are the ones that are obviously amenable, and you take extensions or direct limits, think direct unions, and see what you obtain by doing that. That's all the class of elementary amenable groups. So these are new amenable groups in the sense that you can't build them from the obvious building blocks. Let's break now. Yeah. Any questions? Okay, thanks for coming back. Right, I was hoping to have all of this written down before you came back, but you beat me to it because I wanted to be quick. Well, first of all, this is fulfilling a promise that I made to Jacopo. So we had before the groups that I raised, Gorgiev's groups, Gupta-Sidki groups, they're amenable. And in fact, all the examples I showed you of self-similar groups, except for, well, all of them, all of the examples of self-similar groups that I showed you are amenable. But you can have non-amenable self-similar actions. Here's an example due to Misha Kapovic and Zoran Sunic. And it's a self-similar action of PSL2Z, so the free product of C2 and C3 on the 3 regular tree. So a generator of the cyclic 3 group is just the degree 3, the cyclic permutation at the top. And then the thing of order 2 is this complicated thing. Go figure. That turns out to be PSL2Z. In fact, this is a really nice paper. The main author is Kapovic, but Sunic actually wrote down the calculations for this. So the main result in the paper is, I have to read it out loud because I forget all the words. So if you have an irreducible lattice in a linear semi-simple algebraic group, that has a self-similar action if and only if it's virtually an arithmetic lattice in the Lie group. So, okay. I mean, it has to do with the fact that arithmeticity is constrained about the group structure, and having a self-similar action is actually a property of, I mean, tells you that you have certain subgroups, that there is certain dynamics between certain subgroups that I will not go into. So perhaps it's not too surprising a posteriori, but it's I think a really nice result. You know, which lattices have self-similar actions? Turns out only the arithmetic ones, essentially. Okay, I wanted to give you more exotic examples of self-similar groups as motivation of why we want to study them, and also because I like this result. So I'm going to tell you this result that I like. There are variants, of course. Once you start with a few examples, then people start building more. This is a thing that people do, change examples. So here are variations of the Gupta-Sidky group, or the Gupta-Sidky groups. So you start out with a vector over the field of P elements. There are P minus 1 entries, where P is a prime. Now the group G sub E is generated by, again, A and B. A is still the P cycle as before, but B is now A e to the 1, A e to the 2, blah, 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 A e to the P minus 1, B. So we've just changed the powers of A that we're allowed to do down below. So GP will be for the vector 1, minus 1, zeros. And if you change the vector, you change the group most of the time. Okay, so here's an example. So this is, of course, a subgroup of I sub P star. So this is something that I showed many years ago with two collaborators from Bilbao. So we showed that if E is not the constant vector, then all proper quotients of GE are quotients of GE modulo the stabilizer in GE of level n. So the stabilizer in G of level n is the intersection of all stabilizers of words of length n, as you might expect. So okay. So this is a subgroup of the automorphism group of the tree of depth D. Okay, this is saying every proper quotient, all proper quotients are finite, and you can obtain them by looking at the action modulo levels. Okay, well, that's nice. I like it because it means I can say stuff about all the finite quotients of my infinite group. But so in particular, because of the way that this acts in the tree, I'm only allowed to do P cycles. So, right, I'm not allowed to just swap these two and leave this one fixed. I don't have the full symmetric group as my possible permutations. I only have cyclic groups. And a Reith product of cyclic groups of order P is a P group. The whole thing, GP is a P group, but not all GEs are P groups. Some of them are virtually torsion free. So this means that what did I want to write? That they're all finite P groups. But let me give you an example. So an example is if E is the vector 1, 1, all ones, and then a 0, so that means that B is A, identity B. Then GE, it has well, the index is p squared. Its commutator subgroup has index p squared and is torsion free. But this result about the finite quotients carries over to this finite index subgroup. So this torsion-free, this finitely generated torsion-free group has all finite quotients P groups. Right? Imagine I tell you all finite quotients of the free group have order of power of P. No, that's clearly not true, right? The free group has lots of finite quotients. But just because you're torsion-free, just because every element has infinite order, doesn't mean that all the quotients have to have whatever order you like. So these two things together imply that there exist finitely generated torsion-free groups, all of whose finite quotients are P groups. If you like this language, the profinite completion of there exist finitely generated torsion-free groups whose profinite completion is pro P. That's what this says in a different language. If you don't like profinite groups, forget about what I said. Right. Okay, I should have had the break here, but it was already going on for very long. When am I supposed to end? 15. Oh, 50 past, 50. Okay. Oh, all right. Well, I'll start and see where I get, and then I'll continue next time. Why am I doing this? It's not like the boards go any further down. This is still too high up, but I keep wanting to push and make it come to my height. Okay, so new topic, tree shifts. Okay, if you got lost or bored, now is the time to come back. Okay, there's a big difference actually between these exotic examples and say PSL2Z or like the self interactions of what do I want to call them? They're not normal groups. I mean usual groups. Think other groups that had appeared before. There's a structural difference between these groups, even though they're all self-similar. But before I can get to saying more, I need to make some definitions, and this will appeal to the dynamicists, I hope. So here goes. Let's think of every element of isom D star, every automorphism of the D regular tree can be thought of as an element of sim D to the D star. What do I mean by this? Well, let's do it for the generator of the odometer. How do I obtain this? Well, I look at its, so this is via its portrait. So I had a conversation, someone at breakfast saying that as with people, you will know groups by their actions. So this is one action, but okay, it's not quite the action of the group, it's the portrait. It's what it looks like. So it's the appearance. I like how we play with words in mathematics. So this is acting in the binary tree. What's the portrait of phi? Well, at each vertex, right? So this is saying that at each vertex of the tree, I have to put an element of sim D. What element of sim D am I going to put? I'm going to put whatever phi does to the vertices below the vertex. Okay, so here it does sigma, so that's the swap. Here it does the swap, and on this subtree, it's supposed to do the identity. So I do the identity, 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 and so on forever. I put the identity everywhere here, right? It's sim2 is C2, so it's just sigma and identity. But here I've got another phi. So what does phi do? Well, it does sigma. It does first the swap, and then it does identity, identity, identity. But here it does a sigma, and then identity, and then a sigma, and so on. So the portrait of this phi is a bunch of swaps on this ray and the identity everywhere else. Okay, and that's a perfectly good element of this huge Cartesian product. Watch out. This is, so this tells me that I can write or I can identify the automorphism group of the tree as this huge Cartesian product. That doesn't tell me that the group is a Cartesian product, because multiplication is not commutative in each of these entries, right? It's a huge Rees product. Okay, people are saying yes, so good. Now more definitions. An element of sim D to the Dn is a pattern of size n. So that's just, okay. Here's a pattern of size 3. Okay, just what happens up to depth 3. All right, and I just need this. Okay, I wrote it before. Right, so more things about this. I sum D, which we're thinking of as all the possible portraits, is, okay, I can put a topology on this, right? I can put, okay, so this is Cartesian product, sim D, D star. So if I put the discrete topology in these finite groups, and I take the product topology for the whole product, Tikhonov's theorem tells me that this is a compact set. What's maybe not so easy to see is that this, according to this topology, composition and inversion are continuous operations. Okay, so this is a topological group. But it doesn't matter. So this is a compact. So this is compact. What are the basic opens? Basic opens are cylinder sets. Which are essentially defined by patterns, right? It's the cylinder sets are all the portraits which start with a certain pattern. Okay, good. Basic opens are cylinder sets, which are Z of a certain pattern, and these are all portraits starting with pattern. Okay, now yes, so if G is self-similar, then its closure is a closed D invariant, D star invariant. That's what self-similar means. It means D star invariant. So now I've taken the closure, so this thing is closed. D star invariant, and it's also a subgroup. And this is what I'm going to call a tree shift. So the dynamics people will know this because, you know, instead of taking a bind, if I took a one-array tree, which is just a line, then a subshift or a shift is a shift invariant collection of what I've called portraits, which are called configurations in dynamics, if I'm not mistaken. Okay, so because this is a shift, it's defined by forbidding patterns. Put differently, for people who don't know about this, it's closed. So it's the complement of opens. And therefore, that means, right, these are the opens. Therefore, that means that in order to define this G bar, all I need to do is say in the complement of which patterns it lives. And in fact, these patterns cannot appear anywhere, even, so I've said that a pattern is up to here, but these patterns cannot appear anywhere down below because of the shift invariance. If I had a pattern appearing down here, then I can take the section at this vertex, and that would be an element starting with that pattern. And that should be in my G, but G is not supposed to be in that cylinder set. Okay, so G is defined, it's defined by forbidden patterns. Defined by forbidden patterns that cannot appear anywhere at any height, if you like, of the portrait of any element of G bar. Okay, that's what I just said by the shift invariance. So definition, of course, in dynamics, what it's nice. We like to know, or it's particularly nice if you only have to forbid finitely many patterns. If you have to forbid infinitely many, then how do you write that list? I don't know. It gets hard. So if you only have to forbid finitely many, that's good. So say that a closed subgroup of isom D star is a finitely constrained group and I'll abbreviate this to FC group. If it is defined by finitely many forbidden pattern. Okay, so this is a finitely constrained group is the tree analog of a shifted finite type, but it also happens to be a subgroup, right? It also happens to be a group. We're not just dealing with symbols, where we can actually compose all the configurations and have a group operation, which makes it more interesting, at least to me, because I do group theory. So there are finitely many forbidden patterns, let's say of maximal size S for size. Of course, if you only forbid finitely many patterns, then you can just go to the size of the largest one and then add and then say, okay, I was only supposed to forbid this thing, so I won't forbid any of the stuff hanging from here for the extra stuff. Anyway, you can always, I'm not sure I explained that very clearly, but you can always assume that they're of the same height, of the same size, the patterns that you forbid. So what's an example of this? I only really have one example to give you, which is the automorphism group of the tree. But look, this is the closure of the finite tree automorphisms. Why? Because the finite tree automorphisms, there are things that do an automorphism up to there and then don't do anything here. So what's the closure, or how do you you take the closure? That means you take a limit of a sequence of things that do stuff to some level. Well, eventually you will have described the whole tree. Good, people are nodding, so that's excellent. This is defined by how many patterns? Which patterns? None of them. I don't need to forbid anything. I can put whatever elements of the symmetric group I want in each of the vertices, right? So it's defined by no forbidden patterns, or let's say 0. Or if you want, I allow all patterns of size 1. All patterns of size 1, which is just what you do at a single vertex, are allowed to happen anywhere. And I have, okay, maybe do I have 5 minutes to state the result? Okay. So here's the result by Grigorchuk and Sunich, and I think it's from 2006 or maybe 8. I'm not around about there. S is at least 1, and the following are equivalent. Oh, if you want. Okay. An example which is actually defined by forbidden patterns. Why take the symmetric group? I could take cyclic group. Okay, maybe not for degree 2, right? I could take CP, C3. If I take C3, then that's definitely not S3, right? So my GEs and GPs live inside a group that's defined by forbidding everything that's not in the cyclic group of order P. So the transpositions are forbidden, and everything else in this symmetric group. Okay, so there's a non-trivial example of a finally constrained group. And that's nice because, well, I'll explain. But the thing to notice is that these things, I said before, these things are isomorphic to a symmetric group wreath isom D star, right? So they contain a huge direct product as a subgroup with finite index. And this you can keep replicating down the tree. It might look like this isn't something special, but it is special. And okay, it has something to do with the result that I'm about to state. So the following are equivalent. G, a subgroup of isom D star, is a finally constrained group defined by patterns of size S. This is equivalent to G closed subgroup of isom D star is self-similar. Well, so far, I'm not really saying anything new. Closed self-similar means defined by forbidden patterns. But what's special about the fact that I only have to forbid finitely many? Well, this condition, which I'm going to call red star. The condition says that if I pick any D elements in, not just in G, in the stabilizer of level S minus 1, so that's this S, and I've deliberately changed I've chosen the subscripts deliberately so that you can see that it's different. The automorphism of the tree, which does the automorphism of the tree that does G1 on the first subtree, G2 on the second one, G3 on the third, and thus the identity on level 1, that's a perfectly valid tree automorphism. And if G1, G2, G3 stabilize this level, then the whole thing will stabilize one level more, right? Level S instead of level S minus 1. Why should this be in G? No reason. That's what's special. It's a perfectly good tree automorphism. It doesn't need to be in G. But if it is, that means that my group is a finally constrained group. And then 3, lastly, 3 is that G is the closure of C for some C subgroup of isom D star, which is countable, self-similar, and satisfies condition star. But obviously for C and not G. All right. Oh, I've gone over time. Can I have 2 minutes? Can I? No? Okay, I'll leave it. Well, okay, I'll just state this next time and keep going on from there. But okay, just to show that, well, I'll give it away. The special groups that I defined, so Grigorchuk groups, the Gupta-Sidky groups, these GUEs, their closures are finally constrained. They satisfy, so Grigorchuk's group, Gupta-Sidky groups, etc. They are the C's in part 3 of the statement. Right, so there we have examples of groups that satisfy this. But the other examples that I gave, except for the whole isometry group, they okay. And this means, let's put it this way. Star means that there's a group, there's a strong property satisfied by the subgroups that is definitely not satisfied by Z, the infinite dihedral group, by PSL2Z, by all the other examples that I gave. So the other similar examples that I gave are not finitely constrained because of this subgroup restriction on the subgroup structure. And I will make clear what that is next time. I'll stop there. Yeah. Finitely constrained is an analog of shift of finite type. Yes. Oof. I don't know. That's a great question. I don't know. It's probably written somewhere. And I just haven't read enough literature. I know where to look, and tell you.